Let's go ahead and give this a shot. So this was the equation that we were using. And we were going to solve for V2. All right, so we need our P1, V1, and T1, and then P2, V2, and T2. All right, so it looks like our first pressure is right over here at 1 atm. Our first volume is right over here at 6 liters. Then we have a new pressure of 0.45 atm. And it looks like Jervin got a different answer, but that's okay. We can go through how to calculate it. All right, so we are still calculating the volume. So I'm going to put V2 here for that volume. We don't know what it is, or I can just put a question mark here because we don't know what it is. Then we're told the gas falls from 22 degrees Celsius to negative 21 degrees Celsius. All right, so let's start with T1. You converted 22 degrees Celsius into Kelvin, and what did you get? Anyone want to bravely say what they got for their first temperature, 22 degrees in Kelvin? All right, excellent. Sounds like 295.15 Kelvin, like so. All right, any questions on how we converted that 22 degrees Celsius into Kelvin? All right, and then for our T2, you converted negative 21 degrees Celsius into Kelvin, and what did you get? All right, so it looks like Tasso got 252.15. Did everybody get something similar? Oh, and it looks like Jervin did as well. All right, so 252.15 Kelvin, like so. Let me separate these a little bit. All right, so questions on how we got any of these variables? All right, so let's go ahead and plug in. So it looks like we have 1 atm times 6 liters divided by 295.15 Kelvin equals, and on the other side, 0.45 atm. I'm going to go ahead and put my V2 in another color here. And down on the bottom, 252.15 Kelvin. All right, any questions about the way I set that up? All right, so I'm going to go ahead and calculate this out because it looks like we have a little bit of a difference of opinion in the answers. So first thing I'm going to do is the left side, so 1 times 6 divided by 295.15. And then it looks like we get 0.020, and I'll just go ahead and say 33 for now, giving myself a few digits. And now on the right-hand side, 0.45 divided by 252.15. And it looks like 0.00, I'm going to say 178 times that V2 we're looking for. All right, so questions about anything that I've done so far? So now I'm going to divide both sides by this 0.00178. And we're going to get our V2. I'm going to do 0.020 and just throw in a few figs here. Oops. All right, and it looks like I'm getting, for now I'm going to say 11.39, and we'll talk about sig figs in a minute. And our volume units are always going to match, so we had liters right over here, so this will also be in liters. And we haven't talked about sig figs yet, but I know there was some difference in answers on this one. Any questions on how we got that 11.39 there?
What I did to get V2 alone is that I multiplied both sides by 252.15K over 0.45 ATM, and then I crossed out all the, I crossed out ATM, I crossed out K, and then I was left with L. And then once I had all of that, V2 was alone, and then I just did the multiplication, and I ended up with 13.3 repeating.
Okay, so let's give that a try. All right, so we're just going to do the calculation a slightly different way. All right, so you multiplied both sides by 252.15. And you divided both sides by 0.45 like so.
Yeah.
Okay. All right, so then let's cross out. So 0.45s will cross. And our temperature will cross. So in the end you got, and I'll put it right down here, V2 equals 252.15 times 1 ATM times 6 liters divided by 0.45 times 295.15 Kelvin, and I think I forgot a Kelvin right up here, but something like so, yeah?
Yeah, and then I just crossed out the units, like K and ATM, and then I was left with L.
Yep, and that'll work for our units, so let's cross out those units. So K's cancel, ATM's cancel, and you're right, we're going to be left with L. So now let's take a look at this in the calculator. So 252.15 times 1 times 6 divided by, and now I'm putting parentheses in the denominator, 0.45 times 295.15. All right, so I'm still getting volume equals to that 11.39 liters. Do you want to throw it in your calculator one more time?
Yeah.
Okay. And make sure if you have more than one number in the denominator, you've got parentheses. All right, so other questions on the calculation or how to work this one out? Okay, so we're still going to talk about sig figs in just a moment. I'm going to go ahead and copy this one on in.
Oh, I wrote one of the units wrong.
Okay.
I repeated 252.15 for both. Yeah.
Okay, excellent.
Yeah. Still looks good though. Thank you.
Okay, you're very welcome. All right. Any other questions on the calculation part? Okay, so now let's go back up to the sig fig part. So it is true that the Kelvin does technically go into 3 significant figures, and that's because you have an addition here. Let me come down here. So if you had 22 degrees Celsius plus 273.15, technically when you do this, 22 plus 273 becomes 295. The 0.15 isn't part of the sig figs because our addition subtraction rule says digits after the decimal, and 22 had no digits after the decimal, so this answer wouldn't either. So technically this is 3 sig figs. However, the reason it goes down to 2 sig figs is because there were some other sig fig, there are some other numbers that had 2 sig figs. And those numbers are this one right here and this one right here. Both of these are 2 sig figs, and this is also 2 sig figs. So that's why we're at 2 sig figs. And our final answer would be 11 liters. All right, so any questions on anything here, including those sig figs? All right, so let's see. So the exam is still up in the air, so I am hoping that we can find a way to have you show your work. I know some of the teachers are going to all multiple choice, but I really don't want to do that. So here's what I'm going to say. If it is a multiple choice question, then you don't have to show me this. But if it is a question where I'm asking you to write out your answer, then I would like to see the whole process, but I don't need to see the units like right in here. If you don't want to show me these units, that I'm not worried about. I'm only worried about the units at the very end. These units and the sig figs for your final answer are the ones that I'd be worried about, but I do want to see how you set up your math equation. All right, so other questions? Okay. All right, so next up we're going to talk about the density of gases. There we go. All right, and this is an application of the ideal gas law. So density of liquids, we usually talk about them in grams per milliliter, or for solids, grams per centimeters cubed. And we know that the density of water is approximately 1.00 grams per milliliter. However, that doesn't work very well for gases because gases are very low density. Those molecules are very far apart. That's why we can compress them into canisters. So we can have canisters of CO2, whether that's for filling up your bike tire, for making carbonated drinks, or for using in paintball wars. So here are gases. They do have low density, and because of that, the usual units don't work very well for us. So if we wanted to talk about, say, argon gas, it is about 0.00179 grams per milliliter. Now, if you're in the lab and you're trying to work with your data, that's just not very convenient. So if your thing is gases, you don't want these really small numbers. They're just kind of a pain to work with. So instead, we talk about them in grams per liter. This way, that same argon gas, we can talk about it as 1.79 grams per liter. It makes your life much easier in calculations. So this is a unit you're going to see and a unit you're going to be working with, and that is grams per liter when we're dealing with something like gases that have very low density. So questions on anything here? Okay, so I don't expect you to memorize the density of argon. I'm just showing you this so that you understand why we use this unit instead of the grams per milliliter for gases. All right, so one thing that I do want you to know is how to find the density of a gas. So this equation right over here, this is an equation that you'll want to know. If you forget it, you can derive it from the ideal gas law. I'm not going to torture you with deriving more equations. Oops. Sorry. There you go. Sorry about that. I'm not going to torture you with deriving more equations, but if anybody wants to see how it comes from the ideal gas law, I'm happy to show you that. But for now, we're going to just use it as is, where D is density, P is pressure, and capital N is molar mass. So this is grams per mole, same kind of molar mass we get from the periodic table. R is going to be our ideal gas constant, and T is a temperature in Kelvin. Now, because we're using our R in ATM, you are going to need to have your pressure in ATM like so. All right, so questions on anything so far here? Okay, so we need the density of carbon tetrachloride. So I know it's been a while since our nomenclature days, but does anyone remember how you would write out the formula for carbon tetrachloride? Excellent. So I see a lot of CCl4. Yes, so this follows molecular naming rules where the tetra refers to 4 and tetra is connected to the chloride. So carbon tetrachloride like so. Excellent. All right. So now we're going to be filling into our formula. Density is PM over RT. So first we need our pressure. And right now, our pressure is 714 torr. Let's put this right down here. And we haven't done very much with pressure conversion, so I want to do this one together. So we have a conversion between torr and ATM. For every 1 ATM, how many torr are there? It's the same as millimeters of mercury. And there we go. Excellent. So 760. So that was one of those conversions I wanted you to know. And this is exact. All right, so go ahead and take a moment and calculate out our pressure in ATM. All right, so it looks like Draven is getting 0.939. Anybody getting a similar answer? Excellent. It looks like Juan's getting the same answer. All right, and so is Andrew and Tasso. So 0.939 in ATM. Any questions about this one? How we're getting this? I realize as I look at myself in the little window that I always look like I'm looking up in the corner, and that's because that's where I put my chat box. So if it looks like I have something interesting in the corner I'm always looking at, it's just the chat box. All right. Oops. I'm just going to move this, get this out of our way for a moment. All right, so our pressure, 0.939 ATM. Next up, we need that molar mass. And it is the molar mass for carbon tetrachloride. So let's go to our periodic table. All right, so we are looking for carbon tetrachloride, so 1 carbon and 4 chlorine. So looks like we've got 12.01 plus 4 times our chlorine of 35.45. And Tasso's already got it for me, 153.81, excellent, same value I got. The rest of you calculating along, did you get similar answers? Excellent. You guys can calculate faster than I can. All right. So 153.81, and this is in grams per mole. Okay, any questions on where we got that molar mass? All right, so next up we're going to do R, 0.0821. If you want to use it with more sig figs, you're welcome to. Out of habit, I usually do 0.0821. So this is our liters times ATM over moles times Kelvin. And I forget who it was who asked earlier, when you're in the middle of a problem, I don't need you to write all these units. I do out of habit and to show you, but if you don't want to put the units in until the end, you're welcome to. All right, so there's our R, and finally we need our temperature. So we were told our temperature is 125 degrees Celsius. So what'll that be in Kelvin? All right, so I see 398.15, it looks good. Everybody getting something similar? Yep, it looks like Tasso and Juan. Excellent. All right, so any questions on how we set up our formula with pressure times molar mass divided by R times Kelvin? All right, go ahead and take a moment and calculate out your density. And it looks like Jervin has an answer, 44.2. Anyone want to respond to Jervin? Anyone get a similar or different answer? All right, so I see some 4.42s coming through. So Jervin, if you want to just reach, oh, don't worry, Jervin. We're all here for help each other. But go ahead and try calculating that again. So Jervin, I'm not sure what XD means. Probably a texting thing that I am too old to know. All right, so go ahead and click in to tell me if you need more time or if you're ready. Oh, it's a face closed with an open mouth, a laughing face. Oh, okay. Someone sent me a text with the notation for rolling on the floor laughing, and I had to Google it. And I was like, oh man, I'm old. All right, so it looks like a couple people need some more time. So let's take about 1 more minute for this calculation. While we're waiting, I feel like I know there's some teachers who have lots of chemistry t-shirts. I apparently have lots of chemistry mugs. So this is my mug of the day. It says cats, but spelled out in elements. So it's carbon, astatine, and sulfur there. All right. So let's go ahead and go over this. So it looks like 4.42, and we are in grams per liter. There we go. All right, so any questions on how we got this or the calculations or anything? All right, so let's go ahead and take a break. Sorry, I kept you so long. So it's almost, let's call it almost 6:05. So let's take a break till 6:15. But if you have any questions, I am here. Feel free to message me or just unmute and ask me questions. All right, let's go ahead and get started again. Oops. All right, so here's our next problem, and we are looking at the molar mass of a gas. We're going to calculate that. So here's our problem. A series of measurements are made to determine the molar mass of a gas. So the first thing that's happening is a large flask is evacuated, that's emptied of all of its gas, and it's found to weigh 134.567 grams. The next thing that's going to happen is it's filled with gas. Here's the pressure of that gas and the temperature. And then it's going to be reweighed. So the flask plus gas now has a mass of 137.456 grams. And now we have the flask is going to be filled with water at the same temperature and now it has a new mass of 1,067.9 grams. And they mention here that the density of water at this temperature is 0.997 grams per milliliter. So very close to what we normally say, the 1 gram per milliliter, just giving us a few more sig figs. Then it says assume that the ideal gas equation applies, and we're going to calculate the molar mass of our unknown gas. Okay, I'm going to do a split screen here. Let's try one more time. Okay, so I'm hoping that we can see both the question, and then we're going to make some notes off of what we see. All right, what I want to do is bring out the numbers. So when you get a problem like this, whether it's in the homework or whether it's in a test situation, a lot of times students just freak out because there's so many words there. So the first thing I want to do is grab the numbers out and just make it a more manageable problem. So the very first thing is the flask is evacuated or completely emptied, and it's found to weigh 134.567 grams. So I'm going to take that number, and I'm going to say 134.567 grams, and that is the flask empty. So again, what I'm doing is I'm pulling out the numbers that we need so the problem doesn't feel quite as overwhelming. All right, so now let's go back to our next number. So it's saying it's filled with gas, and it's now at a pressure of 735 torr. So I'm going to say 735 torr, and that is going to be the pressure of the gas. Okay, so let's see what else we can get out of here. So we're at 31 degrees Celsius. So let's write that down. So next up we have the mass of the flask plus gas at 137.456 grams. So this is the flask with the gas in it. By the way, I hope I'm not making you dizzy zooming in and out of the two windows. If it's driving you crazy, please let me know. All right, then it's filled with water, and it's at the same temperature, so I'm not going to bother writing down the temperature because it's the same one. But we have a new weight, and that is 1,067.9 grams. And this is the flask plus water. And then there's one other piece of information that we're given, and that is the density. So the density of water at this temperature is 0.997. All right, so we've taken this, I hate to call it an ugly looking problem, but it is the type of problem that would make students completely freak out if it showed up on a homework or a test, just because there's so many words in there. And we have distilled out the parts that we need. So this is the numbers, and I've got a label with each of them, and so that's really all we need out of that problem. So any questions about what I did or why I did that, just pulling out the numbers that we need to use? So you don't have to do it that way, but a lot of students find that that just makes life a lot easier when you just have those numbers listed out. All right, so that's all of our data. Next, let's talk about what we actually want to do here. So we want to find the molar mass of a gas. So what I find is really helpful when you're not sure where to start is to look at the units. So what are the units of molar mass? Yes, I'm hearing moles per gram. So molar mass equals, oops, instead of moles per gram, grams per mole. So how many grams per 1 mole, essentially? Okay, so there's our molar mass. And now let's take a look at what we've got. So we know how many grams the flask was when it was empty. And we know how many grams it was when it was full. So do we have enough information to find out the grams? The grams of our gas? Yes. Yes, and I'm hearing subtract. Go ahead and do that. Take a moment and subtract these two, and let's get our grams of gas. Anyone want to bravely type in what they got for their mass of gas? All right, so I'm seeing 2.889 from Clinton. Anybody else got something similar or different? All right, so it looks like Angie and Kimberly have the same, and Francis as well. All right, so any questions on how we got our grams of gas? All right, so here are our grams of gas, and where we're going to be placing them is right up here. But we have to find our moles. And let's take a look at what we've got. So we know our pressure, and we know our temperature. And I'm going to tell you we will be able to find out our volume. So what would be the best way to find our moles? If we have our pressure, our temperature, and we will have that volume. And yes, PV equals nRT, exactly. So this is a gas, so you should always be suspicious that you might need that ideal gas law. So let's talk about PV equals nRT. All right, so what we want to get out of here are the moles. We know our temperature, we always know R, and we were given our pressure. So now we've got to figure out the volume. So they've done something in this problem that's very common, and should we be doing a wet lab, which I know we're going to do it online, but if we had been doing it, you would do something very similar in class. So they're taking a flask, like your Erlenmeyer flasks. I apologize, my artwork is not great. Let me try one more time. All right, you're going to imagine that is a perfect flask. Let me try one last time. Yeah. There we go. Third time's a charm. There we go. So there's your flask. So when we want to find the volume of an irregular object, one of the very common ways to do that is to fill it up with water. And I know it sounds weird, but if we fill it up with water, we can then either measure the water in a graduated cylinder, which you would have been doing in lab, or we could measure it on a balance. So it's true that our flasks are usually rated, they are 250 milliliters or 500 milliliters, but that's a very rough estimate. And if you're doing a problem or if you're doing a lab, you want something much more accurate. So here, my blue highlight is approximating water. So again, our two options would be to pour that out into a graduated cylinder, which is not nearly as precise as the balance, or we could weigh this before and after on a balance. So the reason that we don't have you weigh it on the balance in class is that if you spilled water on our balances, it could destroy the balance. So we don't do that in a general chemistry lab, but if you were in a professional lab, you would absolutely weigh it exactly how they're doing it in this problem. That is a way to find the volume of that flask. All right, so let's take a look at what we had for our empty flask. So we're going to use the same number that we did earlier. Here is the flask empty, 134.567 grams. That's the flask alone. Then we need to know about the flask with water. All right, flask plus water, it's 1,067.9 grams. All right, so the first thing I'm going to do is subtract these two to find out how many grams of water we have. So I'm going to do 1067.9 grams, subtract out 134.567 grams. So it looks like 1067.9 minus 134.567. And those of you calculating along, are you getting 933.3? Yep, looks like Andrew got something similar. Excellent. It looks like Angie and Kimberly did as well. So I just used one digit after the decimal, and that's because I'm following the addition-subtraction rule, which says we want the least number of digits after the decimal. So one digit after the decimal with that 9, so I left just that one digit after the decimal. All right, any questions on what we're doing so far? We're finding the grams of water in the flask. We don't really want to know about the water, though. We really want to know about the volume. So now I'm going to say 933.3 grams of our water. Then what I'm going to do is use our density to convert it into volume. And they've given us a more precise density here. This one right over here, 0.997 grams per milliliter. So grams on the bottom, milliliters on the top. 0.997 goes with those grams. 1 milliliter on the top. And because I know we're going to eventually need liters for our PV equals nRT, I'm going to say that there are 1,000 milliliters in every 1 liter. Okay, so take a moment and calculate out how many liters we have in this flask. All right, so it looks like 0.936 is the popular answer. Is everybody getting something similar there? Looks like several of you got that. Excellent. All right, so any questions on how we first found our grams of water and then we took those grams of water and turned them into liters? All right, so this right here is the volume of the flask. So we now have our volume of our flask. So we're trying to solve PV equals nRT. And we're trying to solve it for the number of moles. So we've said the pressure way back here was 735 torr. Which you all are going to convert into ATM. We've said our volume is 0.936 liters. And our temperature is 31 degrees Celsius, which you're going to be converting into Kelvin. And then R is a constant. So what I'm going to have you do is first calculate out N right here. And then what I'm going to have you do is plug it in I'm going to have you plug it into the molar mass. So we know our grams, but you will be plugging in the moles. So first calculate N in PV equals nRT, and second calculate your molar mass by putting the grams that we found on the top and the moles that you will calculate on the bottom. So go ahead and give that a shot. Feel free to message me if you have any questions or message anyone in class. So again, if you need any help, feel free to message me. If you want to talk to anyone else in class, feel free to message them. And feel free to compare answers with others once you have your answer. All right, so feel free to click in if you're ready to go over the problem or if you need more time. All right, so it looks like several of you need more time, so let's go ahead and take another minute or two. Again, those of you who have an answer, feel free to message each other and compare your answers. All right, it looks like Juan put up an answer. If anybody has an answer and wants to answer Juan. All right, so it looks like Clinton got the same as Juan. And it looks like Tasso got something similar. And it looks like Allie got something similar, and so did Angie. All right, so things are looking good, and Dravin's getting something similar as well. All right, so let's go ahead and click in one more time and let me know if you are ready to go over it or if you need some more time. All right, so let's take about one more minute, then we'll go over it together. But feel free to chime in on the chat if you got something similar or different to what's up there. All right, so let's go ahead and give this a shot. So the first thing we're doing is PV equals nRT. So for that pressure, you are converting it into ATM. So you were dividing by 760 torr. You had 1 ATM on the top. So what was your pressure in ATM? Anyone find that pressure in ATM? Looks like 0.967. All right, so any questions on how to get that pressure in ATM? All right, and then for our temperature, you added 273 or 273.15. And what did you get for your temperature in Kelvin? All right, so I'm hearing 304.15. Did everybody get something similar? Sounds like Amber got something similar. Excellent. All right, so let's go ahead and start plugging in. So 0.967 ATM times our volume of 0.936 equals the N that we don't know, that's what we're looking for, times 0.0821. And then times our temperature of 304.15 Kelvin. All right, so any questions about how I set this one up? All right, so what did y'all get for your moles? All right, so I'm hearing 0.0362 or 363. I'll go ahead and go with 0.0363 is probably just a rounding difference. All right, so any questions on how we got this, or anyone want to see me work this out on the calculator? And Tasso, I'm thinking that you just forgot the 3 when you were typing because you've typed in 0.063. Yes, okay. All right, so anybody getting something different or want to see me work this out on the screen? All right. So now we know our moles and we're ready to find our molar mass. So grams on the top, 2.889 grams divided by our moles on the bottom, 0.0363 moles. All right, and what did y'all get for your molar mass? All right, so I am seeing 79.6, and I recall from earlier that most of you got similar answers in grams per mole. So any questions on how we got this answer? Anyone want to see me do any of these calculations on the screen? Oops. All right, so this was actually a pretty tough problem. So when you get to problems like this and they just feel, oh, and Andrew says, which gas is it? And we actually don't know. We can't determine it because we don't know if it's monatomic, just one element, diatomic 2, or it could have any number of elements in there. So we don't have enough information to determine which gas it is yet. All right, so when you get to one of these problems and you look at it and you go, oh my gosh, I can't solve that problem, what I'm going to ask you to do is everybody can pull out the numbers. So start by pulling out the numbers and labeling them. If you're still not sure where to go, think about what you're being asked to do. So in this case, we were asked to find the molar mass. And so I would then just put the units down. So see what we have and what we need. So we could get those grams and we need to find the moles. And considering it's a gas and we're looking for moles, there's a good chance we are going to need that PV equals nRT. If there is a missing piece, like for us, their volume was missing, there was a way to find it inside of there. So again, I would say try not to get overwhelmed. If you see a problem like this, just pull it apart into its pieces, get rid of all those extra words, and it seems a lot more manageable. All right, so questions on anything here? All right, so next up we're going to talk about Dalton's law of partial pressures, which sounds more challenging than it is. So Dalton's law of partial pressure simply says that the total pressure is the sum of the individual pressures of the gases. So every gas exerts its own pressure. Total pressure is just the addition or the sum of those. So it says total pressure of a mixture of gases equals the sum of the pressures that each would exert if they were present alone. All right, so I'm going to give you an example of that. So let's say that we have a container. My containers aren't so bad. They look sort of like containers. All right, and this container has a closed lid. It would have to have a closed lid because there's gases inside. So now let's go ahead and put some gas in there. And I'm going to say that there's some nitrogen there's some argon, there's some oxygen, and just for fun, let's put some xenon in there. So for the nitrogen, I'm going to say the nitrogen alone exerts a gas of, let's say, 0.20 atm. The argon alone exerts a gas of, let's say, 0.5 atm. And the oxygen, let's say it has 0.3 atm all by itself. And let's say the xenon has 1.20 atm. That's the pressure of the xenon all by itself. Okay. So the total pressure, something that we affectionately call P tot or P total, is just the addition of all of these. So if I take 0.2 and I add it to 0.5, 0.3, and 1.20, I get 2.20 atm. So what Dalton's law is telling us is if we add up the pressure from each gas individually, we will get the total pressure inside of this container. Now, when we talk about each gas individually, there's a notation we use, and that is putting a P right here. So what I just did with that PN2, that is saying partial pressure of nitrogen. That means it's the pressure that nitrogen would exert if it was all by itself in that container. I can also say the P for argon, the P for oxygen, or the P for xenon. So we'll be seeing that notation, and again, it just means this is how much pressure the gas exerts all by itself inside of that container, and then P total, or P tot for short, is the pressure that all the gases exert together. And the total pressure is just the addition of all the other pressures. So Dalton's law really comes down to just adding everything together. So any questions on anything here? And anyone need this slide for a little bit longer? Okay. So I just want to go back to this slide for a moment, and I know it looks weird to say P1 plus P2 plus P3. All it's trying to tell you is what I've written out on the next slide there. It's saying you add up all the individual pressures from the gases, and that's how you're going to get the total pressure. So questions on anything so far with this Dalton's law of partial pressure? So by the way, I don't need you to memorize the word Dalton. I just need you to know how this law works. All right, so next up is mole fractions. So here, a mole fraction is the moles of one gas over the total gas. So let me write that one just out in words here. So the moles of one gas over the total moles. And the N that you're seeing there, N just represents the number of moles. So it's kind of a cruel thing that we use N for moles when there's no N inside of moles. But we have so many things that we use M's for. So that N just means moles. I'm going to say number of moles like so. All right. So here we have a gas that's made up of 0.0249 moles of oxygen and 0.0138 moles of nitrogen. We're going to find the mole fraction of oxygen, and then we're going to find the percent of oxygen in the mixture. All right, questions on anything so far? All right, so here were the numbers that we had, the amount of moles of oxygen and nitrogen. And part A said, what is the mole fraction of oxygen? So what I'm going to do for A is take the moles of O2 divided by the total moles. So we're going to say 0.0249. Those are our moles of O2. Divided by our total moles, which will be 0.0249 plus 0.0183. Now it's kind of a weird thing. We call this mole fraction, but you actually have to calculate it out. You actually have to do that division. So if I were to do this division, it looks like 0.0249 divided by, in parentheses, 0.0249, oops, plus 0.0183. And it looks like, I'm going to call this XO2, where X represents the mole fraction of O2, that X, a capital X represents mole fraction, so XO2, mole fraction of O2. And it looks like to three significant figures, I'm getting 0.5, and I guess I'm going to say 76 to keep it at 3 sig figs. Those of you who are calculating along, are you getting similar answers? Excellent. All right, so mole fractions have no units. The reason they have no units is because the moles cancel with the moles. So here is our mole fraction of O2. The moles of O2 divided by the total moles, and again, you do have to do the division. You can't leave it in fraction form. All right, so questions on part A there, the mole fraction of oxygen in the mixture. All right, so part B asks for the percent of oxygen in the mixture. So the percent of O2 the way we're going to get this is we're just going to take our mole fraction of O2 and we're going to multiply it by 100%. So the way I like to think of our mole fractions is, yep, and I heard Tasso say times 100. Excellent. So the way I like to think of our mole fractions is it's just like the decimal version of a percentage. So I'm going to take that 0.576 and I'm going to multiply it by 100%. And it looks like it's going to be 57.6%. And that will be the percent of O2 in our mixture. All right, any questions on how we converted between mole fraction and percent here? Okay, any questions about how we got our mole fraction? All right, so next a little more about partial pressure. So here we have a mixture of gases, and they are at 785 millimeters of mercury. What we know is they contain 82% nitrogen and 18% oxygen. We want to know what the partial pressure of oxygen gas is. And there's a notation down at the bottom, and that is whenever you're given the percent of a gas, we're going to assume it is a mole percent, not a mass percent, because it's really hard to find the mass of a gas. So it would be very unusual to see a percent by mass of a gas. So again, if you see a percent of a gas, assume it to be a mole percent. All right, so what I'm going to do is I'm going to find that partial pressure of O2. So I'm going to write our partial pressure notation, partial pressure of O2. And it is going to be P total, or we often for short call it P tot, times the mole fraction of O2. So the way this is going to work is 785 millimeters of mercury, and I'm going to take the percentage of oxygen but put it into decimal form. So I'm going to call it 0.18. So remember that the mole fraction of oxygen equals the percent of O2 in decimal form. Another way of saying that is that it equals the percent of O2 divided by 100. All right, go ahead and take a moment and find our partial pressure of O2. Anyone find that partial pressure of O2? All right, so it looks like Andrew got 0.18. Anybody else get something similar or different? So you're taking 785 and you're multiplying it by 0.18. Remember what I did right down here? Oops, let me change colors. This mole fraction of O2, that just represents this part right there. So you want to take the 785 times the 0.18, and it looks like several of you got 141.3. Like so. And so Angie has a great question, and what I would tell you is leave it in the unit it's already in unless you have a reason to convert it. So if you have R, you're going to have to go into ATM, or if I ask you to convert it, then you would need to, but in this case, you're not asked to convert it and you don't have R, so I would just leave it in millimeters of mercury. All right, so questions on anything here so far? So just to be accurate with our sig figs, it looks like we're at 18% oxygen, which is 2 sig figs. So I'm going to go ahead and call this 1.4 times 10 to the second millimeters of mercury just for our sig figs because of that 0.18. But any other questions on this one? Okay. So next up we have a gaseous mixture, and it's made from 6 grams of oxygen and 9 grams of CH4. It's going to be placed into a 15-liter vessel at 0 degrees Celsius. What we want to know is what is the partial pressure of each gas and what is the total pressure in the vessel. And I'm going to tell you there's 2 methods for doing this, and it just depends on which way you want to do it. I don't think either one is easier or harder, but we'll look at one way, then I'll show you the other way. So there is a way to change the ideal gas law to look at one gas specifically. So normally we've talked about PV equals nRT, and notice I'm spacing things out here. And normally we've talked about the entire mixture, but we don't have to. We can talk about one gas specifically. So let's say that we want to start with oxygen. There's no reason I could have started with CH4, but I just chose oxygen because it's listed first in the problem. Now what I'm going to do is I'm going to find the partial pressure of O2. So PO2 stands for the pressure exerted by O2 alone. The volume will be the same for both of them. Number of moles for oxygen alone. R will be the same, and temperature will be the same. So the idea is if we modify this so that we only look at the number of moles of oxygen, then we will find the pressure of oxygen alone. So any questions on how I modified that PV equals nRT? Okay, so let's start plugging in here. So we want to find the pressure of our oxygen. So we'll need to know our volume. And it says they are in a 15-liter vessel. So all gases stretch out, they expand to fill the entire container. So it does not matter how big or small the container is, both of the gases will expand it to fill that entire container. So both of them will be 15 liters in volume. Next up, we need to find our N. And what we know is that we have 6 grams of oxygen. So I've got 6 grams of oxygen. How can we find the moles of oxygen from here? How do we go from grams into moles? Excellent. So I'm seeing lots of molar masses. So we'll need to know how many grams of O2 is in 1 mole of O2. All right, and for the molar mass, I'm seeing 16 and I'm seeing 32. What do you all think? All right, so I'm seeing lots of 32s, and it is indeed 32, and the reason is that we have 2 of those oxygens, so we have to add the 16 twice. Exactly, and Jervin says because it is O2. So any questions on why we're using 32 instead of 16? All right, so let's go ahead and find those moles. It looks like 6 divided by 32. All right, so I am coming up with 0.18, and I'm going to go ahead and say 75. These are our moles of O2. Those of you calculating along, did you get something similar? Excellent. I'll go ahead and put this aside like so. Oops. I'm going to put a little box around this just so this is a little aside on how we found, how we found our moles. Here we go. All right, so any questions on how we got our volume or our moles? Okay, so we always know our R. And next up, let's find our temperature. So it looks like temperature is 0 degrees Celsius. So we're going to add 273, or if you like, 273.15. We're going to call this 273, and I'll go ahead and say 273.15 Kelvin like so. All right, any questions on where we got our numbers here? All right, so go ahead and plug this into this ideal gas law and find the pressure due to oxygen alone. Works the same way you would any other time. Plug in your volume, number of moles, R and T, and then solve out for P. All right, so if you have any questions, feel free to message me or message anyone in the class. And when you get your answer, feel free to put it into that group chat. All right, so it looks like several of you are getting similar answers. All right, so go ahead and click in whether you need more time or you are ready to go over it. So let's take another minute or so to keep working, and then we'll go over it. All right, so let's go ahead and go over this. It looks like most of you are getting 0.280 ATM. So any questions on that, or anybody getting something different? Or would anybody like me to work that out on the calculator on the screen? All right. Okay. So we have just found the partial pressure of oxygen, but we have more to solve in the problem. So it wants the partial pressure of each gas. So the next one we're going to do is CH4. So again, we're using PV equals nRT, but now we're doing it for CH4. So again, the pressure and the number of moles are going to be specific to CH4, but they do share the volume, they share the temperature, and R is always constant. So we don't know our pressure, but we said that our volume was 15 liters. We know our R constant, and the temperature we said was 273.15 Kelvin. Now we need to find our moles. So it looks like we have 9 grams of that CH4. So we're going to need our molar mass for CH4. All right, so someone who has a periodic table handy, which hopefully is everybody, but I know not everybody does. So as somebody who has a periodic table handy, do you want to calculate out our molar mass for CH4? All right, so it looks like we got a 16.042, and that looks good. Any questions on how to find the molar mass for CH4? Okay, so I'm going to take 9, divide it by that 16.042, and it looks like we have 0.56, and I'm going to go ahead and throw in a few digits here, 10 moles of our CH4. Actually, we don't need that 0, I'll call it 0.561. All right. So those who calculating along, did you get something similar on your calculator? Yes? Okay, excellent. All right, so let's plug that in for our moles. And let's calculate this one out together. All right, so PV equals nRT, and we're dealing with CH4. All right, so we're trying to find that pressure of CH4. We know our volume to be 15 liters. We know our number of moles to be 0.561. We have our R value, 0.0821. And we have our temperature of 273.15. Scoot everything over a little. Okay. Any questions on how I set that one up? All right. So we're looking for the pressure of CH4. So go ahead and calculate that out and put that in the chat box. All right. So I'm seeing 0.840 or 0.839. Looks like on my calculator I got 0.839, but 0.840 is just fine as well. Any questions on how we got this value? It's the partial pressure of CH4. All right, so just for fun, this is from way back I believe in chapter 1, this is what methane looks like. Or I'm sorry, this is what our compound looks like. I was going to ask you what what's its name is, but I just told you. So methane, meth because it's only one carbon, ane because they're all single bonded. So this is methane. All right, so any questions on how we found this partial pressure for methane? All right, so now we want to calculate out P total or P tot. How do we find our total pressure? So meth meant for, so Jervin, you're saying thought meth meant 4 hydrogens, not 1 carbon. So in organic nomenclature, meth means 1 carbon. And we just assume the hydrogens to be there if they needed to. Yeah. And then ane means the single bond. And I see Juan saying add up the partial pressure. Yep. No worries, Jervin, we're here to learn. All right. So we have 0.839 ATM coming from our methane. And we have 0.280 coming from the pressure of oxygen. All right, so if we add these up, it looks like our total pressure, 1 point, and I'm going to say 119 ATM, and I'm following the sig fig rule for adding, and that is digits after the decimal. So 3 digits after the decimal, 3 digits after the decimal, so I get 3 digits after the decimal. So any questions on how we found our total pressure for this gas? Or I should say the system of gases? Oops. One more time. There we go. All right, so I told you there were 2 methods for doing this. So I'm going to call this method number 1. Okay, and you might be thinking, wow, I'm glad there's a second method. The second method isn't necessarily any quicker. So the next one we're going to call method 2. All right, so if you were doing method 2, you would have P total times the volume equals N total times R times T. So that would be your first step. Once you find P total, then you're going to need to multiply that times your mole fraction of O2, and that will give you the partial pressure of O2. And you will need to multiply that times the mole fraction of CH4. That would give you your pressure of CH4. And the reason that this isn't that much faster, or probably not any much faster, is you've got to calculate out the mole fraction of oxygen and the mole fraction of CH4. So just a different way to do it, where here you find the total first, and then you find the individual pressure second. But either one does work. So any questions on anything here? All right. So next up, we have an application of partial pressures, and this is actually something you would have done in the lab, and I'm hoping we can get a good video because it's a great demonstration of partial pressures. So here what they're doing is they're heating a test tube just like you would have, and they're producing gas, and we're collecting gas into this beaker over water. And you might be thinking, well, that's silly. Why do we want to put it into the beaker? The reason we want to do that is so we can find out how much gas we have. So if you measure the water before in a graduated cylinder, and then you measure it after, the difference in the volume of water is going to be how much gas you produce. That's why this is a really valuable technique. And again, we usually do it in our class. You're going to get some data from it. but also it's done in pretty much every General Chemistry 1 class because it's such a valuable technique. Now we've got one problem with the technique, and that problem is that there's more than one kind of gas in there. Water always vaporizes a little bit. There's always a little bit of vapor pressure. So we're going to need to remove that vapor pressure, and that's where Dalton's law of partial pressures will come in. So right underneath it says when gas is collected over water, there is always water vapor mixed in with the gas. So to find the pressure of the gas you desire, the gas you want, you need to subtract the vapor pressure of water. So this is important. So on a test or a quiz question, if I tell you this was collected over water, you need to subtract the vapor pressure of the water. And I'm going to show you how to do that. But any questions on anything here so far? All right. So here we are collecting gas over water. And here we have a sample of potassium chlorate of exploding gummy bear fame, if you all remember the first day of class. It's partially decomposed, producing oxygen gas that's going to be collected over the water. The volume of gas collected, 0.250 liters, and we're at 26 degrees Celsius. And we have a total pressure of 765 torr. Now, in case you're wondering, how do we find our total pressure? We would be reading the barometer in class. So the room pressure we assume to be the same as the pressure of the gas inside of that container. The reason we can assume that is because at the end of the experiment, we would have asked you to raise or lower your beaker so that the level of water here is at the same level that we have right over here. And once upon a time, long, long ago when we started the chapter, we said that when we were looking at a manometer, if the level of mercury is the same, the pressure of the atmosphere is the same as the pressure of the gas. So we don't use mercury, we just use water, but it's the same concept. As long as we level them out, as long as we ask you to raise or lower your beaker, so it's at the same height as the water in the overall container, the gas inside of your beaker will be the same pressure as the gas in the room. And I know right now you might be thinking, oh my gosh, that sounds like so much fun. I'm so sad that we can't do this. It's actually, I hate to say, but it's actually kind of a pain, and students dislike having to raise and lower to get to the right water level. So we've actually saved you some pain here. Okay, so the room pressure, or the total pressure, is 765 torr, and the vapor pressure of water at 26 degrees Celsius is 25.2 torr. So let's take a look at this problem. Oops, put that in the wrong place. All right, so I'm going to bring all the numbers down. So we know that our volume is 0.250 liters. That was our volume. And we know our temperature to be 26 degrees Celsius. And we know our pressure total, or P tot, 765 torr. And then what we know is the pressure of water alone is 25.2 torr. And the question that we're asked is how many moles of oxygen are collected. So we're going to work this one together, but any questions before we do about anything here? All right. So this is an ideal gas law problem. So what we want to know is how many moles of oxygen we have. So we need the pressure of oxygen alone times the volume. That will give us our number of moles of oxygen times R times T. All right, so we know our volume. Our temperature, we're going to add that 273.15. So I'm going to do 26 plus 273.15. Oops. There we go. All right, so it looks like it is 299.15 like so in Kelvin. I'm going to convert our pressure. Actually, before I convert the pressure, I'm going to go ahead and do our subtraction because they're both in torr right now. And I'm going to take a look at these right here. Oops. All right, so what we know is that P total will equal the P from our oxygen, the pressure from the oxygen, plus the pressure from our water. Now I'm just going to solve this for the pressure of oxygen, and I'm going to say the pressure of oxygen equals P total minus the pressure of the water. So I'm solving this out. However, as a previous PowerPoint said, it's easier to just remember that when you're collecting over gas, the pressure of oxygen will be P total, which is the room pressure, minus the pressure of H2O. And this PO2 in our lab is referred to as the pressure of dry oxygen. Or the pressure of oxygen dry. The reason we use the word dry is we are removing the water. We're removing that pressure of the water. So the way that we're going to do this, we're going to find the pressure of essentially our dry oxygen after the water has been removed. I'm going to take the total pressure, 765. And I'm going to subtract out the pressure of water. And here that's 25.2. All right, so I'm going to take that 765 and I'm going to subtract 25.2. And it looks like we are at I'm going to say 739.8, like so. And this is the pressure of our oxygen. Okay, so any questions about what I did here or why I had to subtract out the pressure of that water? Okay, so for our problem, we have one more step, and that is we got to get this into ATM. So here I'm going to take our pressure of oxygen, 739.8 millimeters of mercury. And I'm going to divide by 760. And it looks like we're getting 0.9, I'll give it 0.973 ATM to 3 sig figs, because we really should have had 3 sig figs here. Okay, so any questions about anything I did here with this removing the water from the total pressure? All right, so we are just about ready to solve our problem. We finally have our pressure, 0.973 ATM. All right, so any questions about anything that we have so far? Let's see, so Eddie, you're wondering, so it was, oh, I hear what you're saying. I'm sorry, I use them interchangeably, and so I didn't even think about that. Thank you. Yeah, I just switched over to millimeters of mercury just because that's what my brain did. They are equivalent units, though. For some reason, I did not want to give the Torricelli who discovered torr credit, and I switched over to millimeters of mercury. It's my bad. I'm sorry. All right, other questions so far? Okay. So let me move all this out of our way. Something lost a G for grams. All right. Okay, so let's go ahead and plug in here. So the pressure of O2, 0.973 atm. So we said our volume was 0.250 liters. And then our number of moles of O2 we don't know yet. R, 0.0821 liters times atm over moles times Kelvin. And finally, our temperature, 299.15 in Kelvin, like so. All right, any questions on how I set that one up? All right, go ahead and take a moment and solve out for the number of moles of O2. So when you get an answer, go ahead and type that into the group chat. Oops. All right, so it looks like Angie got an answer. Anybody else get a similar or different answer? All right, excellent. So we're getting some similar answers. Excellent. So getting a lot of similar answers here. So I did get a similar answer as well. 990 moles, and that could also be written 9.90 times 10 to the negative 3 moles, like so. All right. Is everybody getting a similar answer here? All right, excellent. All right, any questions on how we got this answer? All right, so I know I kind of walked you through this one, and if you're thinking, oh my gosh, that problem was so much fun, I can't wait to try one of my own. So when we get to Lab 5, which we will do next week, you will get an opportunity to do this with some lab data. And of course, there's post-lab questions. You're going to get to play with this as well. But any questions on what we've done here? All right, so let's go ahead and take a 15-minute break. When we come back, we're going to work on Lab 8, our day 2 of Lab 8. So let's come back at 7:45, and I will be here. If you have any questions, just feel free to unmute yourself and talk or type into the group chat.